the other box has a plus b x's and minus 2a minus 3b constant term. And so if the two polynomials are the same, you get from one polynomial equation to other equations. You get that the number of x's in one polynomial equals the number of x's in the other polynomial, and the constant term of one polynomial equals the constant term of the other polynomial. And so here we get, here that tells us that the constant term of x minus 4, which is 1, the coefficient of x here is 1, equals the coefficient of x here, which is a plus b. And the constant term on the left polynomial, minus 4, is equal to the constant term on the right side, which is minus 2a minus 3b. And so you get these two equations. See this? Okay. Okay, and so that gives us the following two equations. Okay, 1 equals a plus b, negative 4 equals minus 2a minus 3b. Okay, if you've ever taken linear algebra, then this would be finding all the solutions to a linear system, to a system of linear equations. But you may have done this maybe in junior high school or something. A problem this simple, it gets more complicated. A problem like this, you could solve for a and b by adding certain multiples of one equation to the other to single out one variable and then solve for that variable, then plug in to get the other variable. So for instance here, if I took 3 times the first equation and added it to the second equation, the 3b plus minus 3b would cancel. And then you'd get a equals minus 1, right? Okay, so if you add 3 times the first equation to the second, you get, so 3 times the first equation to the second. So 3 times 1 plus minus 4 is minus 1. 3 times this is 3a plus 3b plus this. 3a plus minus 2a is a. 3 times b, 3b plus minus 3b is 0. And so the b's cancel. I chose 3 on purpose. That way the b's would cancel. So if you add 3 times the first equation to the second, you get that a equals minus 1. Now, plug in a equals minus 1. Plug in a equals minus 1 into the first equation, let's say. You could plug into either one, into the first equation, and solve for b. You get that b is equal to, so if a is minus 1, you plug it in here, 1 equals minus 1 plus b. You get that, so you get that 1 is equal to minus 1 plus b, or that b is equal to 2. That's it. Okay. So now that we found that a equals minus 1, you just put that in here, and then you get b equals 2. Okay. So now we solve for a and b. After we are done solving for a and b, we see that, so before we had that this thing was equal to this plus this, right? Where it was of that form by the partial fraction decomposition theorem. So what was left was we didn't know what the values of a and b were. We've now solved for a and b. A is minus 1 and b is 2. And so that means that this the integrand is equal to the sum of these two simpler fractions. And so the problem of integrating this original integral using properties of integrals is now reduced to integrating these two. Okay, so by substitution, we get that our original integral we want to find is equal to the definite integral from 0 to 1. And then this, right? This is now the new integrand. And so we're going to substitute this whole thing for that proper rational function. And so I'm just going to plug that in right here. See that? I'm just substituting this for this. And then by properties of the definite integral, this is now equal to the first integral. This is from 0 to 1. I'm going to write 2 minus over x minus 2 first, dx, and then that way I can write minus the definite integral. Because this is a negative this plus this, so I'm going to put the positive here and then the minus the other one. That way it's one thing minus the other instead of plus minus one. It's easier to visualize this way. Okay, so it's the minus sign I moved in front of this integral and I put it at the end. This 1 over, so just some algebra here. Okay, so now I have that the original definite integral is equal to this definite integral minus that one. And then if you've already had some practice, if you already practiced doing this in the homework, then you can see that this definite integral is 2 times ln of the absolute value of x minus 2, evaluated from 0 to 1. Okay, and so that's 2 ln of the absolute value of x minus 2 from 0 to 1. That's good. And then minus ln of the absolute value of x minus 3, evaluated. I was helping somebody get into the room. Okay. Go 0 to 1. And now this is equal to, so you just plug in the values. So when you plug in 1, you get 2 ln of the absolute value of minus 1 minus 2 times ln of the absolute value of minus 2. Okay. And so, okay, so I don't think someone's talking to me. I think they're talking to someone else. Okay, so now this is minus ln of the absolute value of minus 2 minus ln of the absolute value. You plug in 0, right? And you get minus 3. Okay, so these are all the calculations involved. Here, I'm plugging in. So when you plug 1 in here, you get 2 times that ln of 1 minus 2, which is minus 1, and then minus 2 times ln of 0 minus 2, which is ln of absolute value minus 2, minus then you plug in 0. Is someone asking a question or? Okay, so then absolute value of negative 1 is 1. ln of 1 is 0. And so this is 0. This is minus 2 ln of the absolute value of 2. And then this is now minus ln of the absolute value of 2. Because ln of absolute value of minus 2 is the same as the absolute value of 2 here. This is minus, which is plus ln of the absolute value of 3. Because the absolute value of minus 3 is the same as the absolute value of 3. Okay, and so then this minus this plus that, that's equal to minus 3 ln of the absolute value. Okay, and then it's equal to minus 3 ln of the absolute value of 2 plus ln of absolute value of 3. And that's the final answer. Okay, you could simplify. Yeah, you can simplify that. You don't have to, but you can simplify that. You could say that this is equal to ln of the absolute value of 2 raised to the negative 3 power by the third law of logarithms. You can move this as an exponent here. And this is plus ln of the absolute value of 3. Then this is ln, the first law of logarithms. You can see this is ln of a product is the sum of their corresponding logs. So this is 2 to the negative 3, and then times 3. See that? And then close parenthesis. Other way. There we go. Okay, and then checking to make sure this is good. This is good. And so then this is equal to ln of the absolute value of 3 times 2 negative 3. That's 3/8. Okay? And so that's another way you can view it. This is equal to ln of the absolute value of 3/8.
Professor.
Yeah?
So we must simplify that answer, or we could just stop at like -3 ln 2 plus.
No, it's right. If you stopped, I would prefer this simplification, -3 ln of absolute value 2 plus, at least that far, because you can combine terms very easily, right?
Yeah.
Going into the extra work of writing this as one logarithm, in this problem doesn't matter. In other problems, it'll matter. Like if sometimes when you're in the middle of a problem and you ask yourself, should I simplify something I found or not? If the problem is going to keep going, if you don't simplify, it may make doing the rest of the problem harder. Here we're at the end of the problem, right? You have an answer and you either simplify or you don't. Their simplification is sometimes not as important to me. But when you're doing a solution, sometimes you need to simplify to just keep going with the problem. If the problem is simplify a logarithmic expression, then the question is to simplify it, and you need to simplify it. If it's just the part of the answer, it may not care as much. Does that answer the question?
Yes.
Okay, you're welcome. Sometimes simple questions can be a little complicated because I'm trying to answer it in all situations, and things are fluid, things change depending on where we're doing something. Any other questions about the homework? Okay, let's keep going because these problems take a while to solve and explain, so better not to do too many of them. Need to continue. Okay, so that's explaining that problem. So I hope I answered. I think Samantha answered the question.
Yeah, that was really helpful.
Oh, okay. You're welcome. Yeah, it's good that you asked this question because this one is simpler than some other problems. So this is a good place to start understanding the partial fraction decomposition theorem and using the partial fraction method, because you build on this by when you have quadratic factors in the denominator and you have repeated linear factors and repeated quadratic factors, and get only a little more complicated. Most of it is this. So if you know how to do this, that's most of it. And then there's little things you add on. There's little intricate details for other problems that make it slightly more complicated, but you're just building on this method for this simpler problem. Okay, let's keep going. Okay, so 6.4. So 6.4 is on integration tables. And so, there's tables that you can use to find values of integrals. So I'm not going to spend much time on this. I think this is something we can kind of we can just kind of move past this one. But so this is integration with tables and computer algebra systems. This is the title in the book here. Okay. So the kind of problem you might see is this problem. It says use the table of integrals to find this integral. Right? It involves looking at a table and then saying, by referencing a table, what is the value of a somewhat complicated integral. So I don't really like this this section that much. So you have the integral of x squared over 5 minus 4x squared. I guess the skill of being able to look something up and to reference something is important, but it's not really an independent thought to look at a table and read what it says. Okay, so in the book, there is a table of integrals, and for this one, you use number 34. Okay, in the table. Okay, because that's the one that most resembles this one. Okay, And so that's the idea. Okay. So look, I'm not gonna put here example one. I'm gonna put the idea of example one. The idea of example one is that you use a table of integrals to calculate this. In the book, there's a long table of integrals, and here you look at the list and you find number 34 matches this one, and then you apply. I think there's over 100. There's like 120 or even more than that. And so this is number 34, and then you match it up and you solve it. Okay. Okay. I want to keep going. So let's go to 3.5. The section kind of stands independent of everything else. So let's go to 6.5. 6.5. Okay. Anything I want you to know is from the lesson or homework, right? So if I don't cover any more 6.4, then you don't have to worry about knowing more about 6.4. Okay. If I want to teach more in 6.4, I'm going to go back to it. If not, then you don't have to worry about it. Okay. So approximation integration. Okay. So it is what it sounds like. We're going to approximate the value of an integral. Okay. And so there are two situations where it is impossible to find the exact value of a definite integral. Okay. Okay. So the first situation is that so the first situation arises from the fact that in order to find the definite integral from a to b of f of x dx using the evaluation theorem, we need to know an antiderivative. Okay, so if you look at this definite integral, the definite integral from 0 to 1 of e raised to the x squared power. So it's e raised to the x squared power dx. So, I mean, you could say it's quite complicated, e to the x squared, but e is a known number and x squared is kind of known. So e x squared you can get kind of easily if you think about it. But if you try to integrate it from 0 to 1, there's a problem. You need an antiderivative of e to the x squared, and there is no known one. Okay. And so there's one example where you can't integrate it because you can't find an antiderivative of the integrand function e to the x squared. So another integral where the same problem arises is this one. The definite integral from -1 to 1 of the square root of 1 plus x cubed dx. So here, you can't find an antiderivative of the square root of 1 plus x cubed. And so since you can't find an antiderivative, you can't use the evaluation theorem, okay, unless you know an antiderivative. All right, so that's the first situation. Second situation. Second situation is when the function is determined from an experiment, from a scientific experiment, through collected data. Okay, so there may be no formula for the function. Okay, so you may not have a distinct formula that tells you the values of the function because you just wrote down data that you found, right? And so you have a table or you have a function. You have a function that represents the data you collected, but you don't have a formula, which means you can't integrate. Okay, so in both cases, we need to find approximate values of definite integrals. Okay, and so we're going to approximate. We're going to approximate this definite integral by we're going to approximate values of the definite integral. Okay. Okay, and so this is how we're going to do it. So recall that the definite integral is defined as the limit of Riemann sums. Okay, so that means any Riemann sum could be used to approximate the integral. Okay, and so the value of a definite integral is the limit of a sum of areas of rectangles. Now, if you go far enough into the sums of areas, they're getting closer and closer to the actual value. And so you just want to go sufficiently far out into the limit so that the sum is very close to the actual value of the definite integral. So let me just quickly illustrate this again to remind you. Okay, so if you have, right, when you calculate a definite integral, let's say the definite integral is y equals x squared. I mean, the graph is y equals x squared, right? And you want to evaluate the definite integral from 0 to 1 of x squared dx, right? Which is the area from 0 to 1 underneath the curve, right? This area here. This is a point here. There's no gap here. Okay. And so you have your approximating rectangles, right? So if you had two approximating rectangles, let's say you had 4 approximating rectangles. Let's say we used right endpoints. Okay, so using 4 rectangles, right endpoints, the lengths at the bottom are the same. You get these 4 approximating rectangles, right? And so if you add up the areas of these rectangles, then you see that the areas of these rectangles, the area of that shaded region, the sum of the areas of those rectangles is kind of close to the area under the curve. It's a little extra, right? There's a little bit more above it. And if you take more rectangles, applying like the same technique here, and you still want to calculate this definite integral. And so you have from 0 to 1, but instead of 4 approximating rectangles, you use 8. Okay, 2, 4, 2, 4. Okay, so then I use right endpoints again. So now I'm going to use right endpoints. I'm going to try and draw this with my hand on the screen as best I can. Right, so using right endpoints, and you're finding the value. Okay, so now we have 2, 4, 6, 8. Okay, so I tried to. There's no space here. This is all combined. Okay. Oops. Okay, I need to move that. Okay. There's no gap here, right? So these are rectangles that. Okay, so you have these 8. So you see that the sum of the areas of these 8 rectangles is closer to the actual area under the curve. This is the end here. They moved the box, so that's the right endpoint. Okay, so if you take the sum of the areas of these 8 rectangles, it's closer to the actual. See, there's only a little bit extra here. While here there was more extra, right? So you see that when you calculate this definite integral, the limit of the sum of areas of approximating rectangles. And so as you get close, as this number increases appropriately, where the maximum value of these intervals is getting smaller and smaller, approaching 0, the sum of these areas is tending closer and closer to that. And so if you want to know the actual area under the curve, you can just look far enough into this limiting process so that these rectangles, maybe 8, maybe 1,000, you add them up, it's very close to the actual area. And you can get arbitrarily close. You can get as close as you want to the actual value, because the actual definite integral is the limit of these sums. And so it's the limit. And so that means that we can go get as close as we want to the actual value. Without, we don't get to the actual value. Maybe we could, but it depends. If it's a very easy function, you can. But even if you can't get the exact value, we know that you can get as close as you want to it without getting the actual value. Okay, so that means any Riemann sum can be used to approximate the integral. So if we divide the finite closed interval a comma b into n subintervals of equal length, and that equal length is delta x. Which equals b minus a over n. Okay, then we get, and we have then the def integral from a to b. Let me check and make sure the sound is good. It sounds good. Of f of x dx is approximately I equals 1 to n of f of x sub I star delta x. Okay, so if we divide that into n subintervals of equal length, then you get that this is approximately that sum. Okay. Where x sub I star is right any point in the ith subinterval. Okay, so you can choose these points x sub I star appropriately to get. So you can choose appropriate x sub I star so that we get the equation def integral from a to b of f of x dx is approximately L sub n, L sub n, which is equal to the sum from I equals 1 to n of f of x sub I minus 1 delta x. Okay, so if you use left endpoints, if you choose these x sub I star to be left endpoints of each subinterval, you can say that the def interval is approximately the left endpoint approximation. This is, remember, this is called the left endpoint approximation. This is from Math 151. Okay, so this is the left endpoint approximation. And so basically what I'm saying is that you can approximate the value of a def integral with its left endpoint approximation. Okay, also, okay, and so let me make a point. I guess I'm going to say this also. If f of x is greater than or equal to 0, then the integral represents the area, represents an area, right? The area under the curve, and it represents an area, and the above represents, meaning this thing. Okay, so I'm going to call this 1. And by above, I mean 1. The above 1 represents an approximation of this area. Oh, that's not where the one. I want the one here. Sorry. That's what. All right, that's one. This represents an approximation of this area by rectangles. Okay, as illustrated on the whiteboard. Right, when I drew those rectangles, right, that's an example of I drew right endpoint approximation. As illustrated for the right endpoint case on the whiteboard. As illustrated similarly for the right endpoint case on the whiteboard. So also we have the left endpoint approximation, and you can also use the right endpoint approximation to approximate your definite integral. Okay, so after all the things I'm saying, what you need to worry about is that you can use the right endpoint approximation and the left endpoint approximation to approximate the value of your definite integral. Okay. This is 2. Okay. So 1 is the left endpoint approximation. 2 is the right endpoint approximation. Those are both approximations of the value of your definite integral. Okay. So the equations defined by 1 and 2 are called the left endpoint approximation and the right endpoint approximation, respectively. Okay, meaning 1 is the left endpoint approximation and 2 is the right endpoint approximation. Okay, so I put that next to it, but I'm also saying it here. Okay, and so I'm going to underline this left endpoint approximation, right endpoint approximation. And so both of those can be used to approximate the value of a definite integral. Okay, so we see from everything above that, so the conclusion to all that is that the left endpoint and right endpoint approximations, so left endpoint and right endpoint approximations can approximate the value of a definite integral. Okay? That's everything that we just did there. Okay. Okay, and so we didn't just have a left endpoint approximation, a right endpoint approximation in Math 152. We also had what was called the midpoint rule. Right? And so the midpoint rule said that if you had a definite integral from a to b of f of x dx, that this is approximately m sub n, which is equal to delta x times delta x times f of x sub 1 bar. There we go. Okay, now I got it. Okay, so I'm going to copy this. Hold on. Now I got it. There we go. Okay, good. Okay. This is x sub 1. There. Good. Okay, so we have delta x times f of x sub 1 bar plus f of x sub 2 bar plus dot 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 plus f of x sub n bar. Yeah, that's the midpoint rule, where delta x is equal to b minus a over n. And x sub I bar is equal to 1/2 times x sub I minus 1 plus x sub I. And that's equal to the midpoint of the closed interval x sub I minus 1 comma x sub I. Okay, so the depth integral is approximately m sub n. M sub n is you take the midpoint of each subinterval, take the height of the function at that point, and multiply it by the same base. And you get the sum of these rectangles. That's the midpoint rule. And so I'll quickly remind you of this from the whiteboard. So the midpoint rule is, for instance, if you have the x-axis, you have the y-axis, you have y equals x squared. You're going from 0 to 1, right? And let's say you use 4 rectangles, right? But instead of the points being the left to right endpoints, you're taking points to be the midpoints of each subinterval. And so here, the height of this rectangle is at the midpoint. The height of this rectangle is at the midpoint. The height of this rectangle is at the midpoint. The height of this rectangle is at the midpoint. And so now you're determining the heights of your approximating rectangles by the midpoint of each corresponding subinterval, right? These are the subintervals on the x-axis that are the base of each rectangle. And the length, again, the length of this subinterval, right? The b minus a, this is a, and this is b, right? And so when delta x is equal to b minus a over n, that means that you're taking the entire length, in this case 1 minus 0, which is 1, and you're dividing it by the number of rectangles you want. So if you had 4 rectangles and the total length was 1, if you want to divide 1 into 4 equal parts, you do 1 over 4, right? And so that's an n. So that's b minus a over n, right? That's delta x. That's the length. That's one way you can define the subinterval, the base of each rectangle, by just being an equal part of the entire length here, right? 4 rectangles, if you want each base to be the same, and the entire thing is 1, you would divide 1 by 4. If the entire length was 2, then you have 4 rectangles, 2 divided by 4, you get each would be 1/2. Now you're just subdividing the total thing into how many rectangles you want the same length. That's one way to define the rectangles. Okay, so this is the base. Delta x is the base of each rectangle. And so that's the base. And then each of these is the height. So x sub 1 bar, f of x sub 1 bar would be, so x sub 1 bar would be the point on the x-axis. That's the midpoint of the first subinterval. X sub 2 bar would be the midpoint of the second interval. X sub 3 bar would be the midpoint of the third. X sub 4 bar would be the midpoint of the fourth. F of those values are the heights of the function y equals x squared at those points. So f of x sub 4 bar is the height of this dotted vertical line. F of x sub 3 bar is the height of this vertical line. F of x sub 2 bar is that, and f of x sub 1 bar is that height. And so that height of the graph at the midpoint of the subinterval, that's going to be the height of the rectangle whose base is delta x, b minus a over n. And so the area of this rectangle is delta x, b minus a over n, delta x times f of of x sub 4 bar. So for instance, the area of that guy would be delta x times f of x sub 4 bar for the x. So x sub 4 bar would be this point. F of x sub 4 bar would be the height of the rectangle, and delta x would be the base. Base times height is the area of a rectangle. It's the area A4, the area of the fourth rectangle, would be delta x times f of x sub 4 bar. Now, if you want to add all four of them, you could say the total area was delta x times f of x sub 1 bar plus f of x sub 2 bar plus f of x sub 3 bar plus f of x sub 4 bar. By distributing the delta x, you're getting the sum of n products. The sum of n products is the sum of the areas of the n rectangles. Delta x times f of x sub 1 bar is the area of the first one, plus delta x times f of x sub 2 bar is the area of the second one, plus dot dot dot, plus delta x times f of x sub n bar is the area of the nth one. And so adding the areas of the n approximating rectangles using the midpoint rule is an approximation of the actual area under is the approximation of the actual definite rule. Okay, this formula is just telling you how to find delta x, and this formula is just saying, well, x sub I bar is the midpoint of this subinterval, because you can find the midpoint by just adding the two endpoints and then dividing it by 2, finding the average. If you find the average of x sub I minus 1 and x sub I, you're finding the real value in between, directly in the middle of them, right? That's just x sub I minus 1 plus x sub I divided by 2 or multiplied by 1/2. Okay, so that's the midpoint rule. It's an approximation of the definite integral using these approximating rectangles. Okay. Okay, and so a lot of the time, not always, a lot of the time, this doesn't have to be always, but a lot of the time, m sub n is a better approximation than L sub n or R sub n, and R sub n. It's better than both. Okay. And so your graph is changing along the interval, right? And so if you're taking the midpoint instead of one end or the other, instead of going to extremes all the way to the left or all the way to the right to define the value, if you said you do in the middle, a lot of the time it results in a better approximation than either of them. Not always. Sometimes you'll actually get a better one using the left or right one. You can construct such functions where any of the three are the best: left endpoint, the right endpoint, or the midpoint. Okay. All three of them are approximations. And so the midpoint rule also gives you an approximation of definite integral. Okay. So you can use so conclusion here, the fact, actually I should say the fact here, is that the midpoint rule also can be used to approximate the value of a definite integral. Okay. Okay, and so now this is the approximation. It's approximately this. Approximately. All right, and so that's another approximating method. We have 3 approximate methods so far: left endpoint rule, right endpoint, left endpoint approximation, right endpoint approximation, and the midpoint approximation. So midpoint rule / approximation can also be used to approximate the value of a definite integral. Okay. And so there's another one, and that one's called the trapezoidal rule. And so you can also use the trapezoidal rule to approximate the value of a definite integral. And so, for instance, if you have, again, the same definite integral, general definite integral, you can say it's approximately, that it's approximately 1/2 times the sum. Let me just help myself out here. Okay. You could take, oh, no, let me put it this way. You can take the left endpoint approximation, which is that. Plug that in here. Add to it the right endpoint approximation. Add to that the right endpoint approximation, and then multiply by 1/2. You can find the average of the left and right endpoint approximations. Okay, and if you do that, that's another approximation. It's called the trapezoidal rule. Okay, so this is just the average of the sum. This is the average of the left endpoint approximation here, the left sum, and the right sum, which is the right endpoint approximation. Okay, and so let's just do some algebra just to simplify this expression. Now this is equal to the delta x factors out. And so since you can factor out the delta x and you have a 2 here, the denominator is still the 2 from the 1/2. And the numerator for this fraction we're going to put in front is the delta x we factor out. And now the rest of it is we have this sum. Where it's plus f of x sub I. So I'm going to put another parentheses here. Okay, so if you add up the 2, you could then write the sum of 2 sums as one sum because the indices are the same. So you could say that the sum from I equals 1 to n of f of x sub I minus 1 plus f of x sub I. The delta x's were factored out and moved here. So now we have that's equal to that. And now continuing. So we still have this fraction in front. Okay, and now inside here, let's see what happens. So when I equals 1, you get f of x naught. And you get a f of x naught here, and you get a plus f of x sub 1 here. This is from I equals 1. See, x naught and x1. And then plus, and so this is from the first term, that first bracket. Plus, now in the second bracket, I'm going to put when I equals 2. So you get f of x sub 1 plus f of x sub 2. That's for the second bracket. Plus, when I equals 3, you get f of x sub 2 plus f of x sub 3. Okay, and then you keep going until you get to the last term. So it's plus dot 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 plus. Now the last term is when I is n. So you get f of x sub n minus 1 plus f of x sub n. And so that is the last term in the sum. All right. Okay, let me see if I can move this. Never mind. This won't move. Ah, there we go. Okay. So now we have the sum of those n terms, right? Now, if you see here, so what happens is you see the f of x sub 1's repeat, the f of x sub 2's repeat, the f of x sub 3 will repeat, the f of x sub n minus 1 repeats. There's 2 of each of them. Then only the f of x naught and f of x sub n is 1. Everything else has 2. So I'm going to write that here. So now this is equal to delta x over 2 times f of x naught plus 2 f of x sub 1 plus 2 f of x sub 2 plus 2 f of x sub 3 plus dot 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 plus 2f of x sub n minus 1, and then plus f of x sub n. Okay, so these two, there's only one of them at the end, and in between, everything's 2, including the things in the dot, dot, dot. Okay, and so that is the trapezoidal rule, that this def integral is the average of the left and right endpoint approximations, which is equal to this. Okay, so the trapezoidal rule says the def integral, this def integral is approximately this. Where?
Professor?
Yeah.
Why does the f of x to the n subscript? Why doesn't it have like a times 2?
The f of x not here?
Yeah, and that one too. The first one and the last one. Why aren't they multiplied by 2?
Okay, so let's go back to the beginning. Right. So what I'm saying here is that this def integral is approximately the average of the left endpoint approximation and the right endpoint approximation. It means it's 1/2 times their sum. So 1/2 times their sum means that you're adding a bunch of things in both of them where everything's being multiplied by delta x. So I move delta x out and I get delta x over 2 times the sum from I equals 1 to n of f of x sub I minus 1 plus f of x sub I. Is that good? Does that make sense so far?
But why is the beginning and the end not multiplied by 2? Or why was it multiplied by 2?
Right, no, but I'm just saying so far. Does it make sense up to
it
this
makes
point?
sense so far, yeah.
Okay, so now plug in I equals 1, right? What is this when I equals 1?
That's f of 0.
Well, read
that's
out the
the
whole thing.
initial.
What is this? What is this? You know what I'm saying. What is this when I equals 1?
When I equals 1, f of x to the I minus 1 plus f of x I.
Right, but plug in I equals 1. 1 minus 1 is 0, right? And
Yeah. So x subscript 0 would be the initial value.
Oh, well,
right?
so when it's x subscript 0, say x naught. When it's x subscript 1, say x1. So x sub 0 is x naught. X sub 1 is x1. X sub 2 is x2. Okay. So read this. Tell me what that is when I is 1.
F of x subscript naught.
F of x naught.
X of x naught, yeah.
So read again. Read the whole thing again. When
so
I is 1.
F of x naught plus f of x 1.
So you see that's the first term here?
Yeah.
Okay, now plug in I equals 2. What do you get?
F of x 1 plus f of x 2.
See, that's this?
Yeah.
Now plug in I equals 3. What do you get?
F of x 2 plus f of x 3.
Okay, now plus dot dot dot. You're doing from I equals 1 to n. Now tell me when I is n. What is this?
F of x n minus 1 plus f of x n.
Yeah, that's this. And so
yeah.
Put the parentheses there. See that? Okay, so now this sum is the sum of everything inside this big bracket. Does that make sense?
Yeah, that makes sense.
Okay, now that we're adding up all these things, look, see what happens. F of x naught appears once here. It never repeats again, right? Because indices go up. Now f of x sub 1 is added to f of x sub 1.
Okay, I get it.
Get it?
That makes sense. Yeah.
And this f of x sub n minus 1 was repeated previously in the previous sum. So there's two of these guys. And now this one, there's only one of.
Oh, okay, that makes sense. Thank you, Professor.
You're welcome. Okay, so now this def integral is delta x over 2 times that sum, where all the coefficients, these are called coefficients. The coefficients are 2, except for the first and last coefficient, which is this one. Okay, so that's where delta x is equal to b minus a over n. Just copy and paste. Yep. Delta x equals b minus a over n. And x sub I is equal to a plus I times delta x. This is from Math 152, Math 151, when you have to find the x sub i's. You start at the beginning a and you keep adding the intervals to get the next endpoints. Okay, so the trapezoidal rule says that this differential is approximately that, where delta x is b minus over a, and an x sub I is a plus I delta x. That's the trapezoidal rule. And so this is a fourth approximation in this lesson of the def integral. Okay, and so we now have four approximating methods. We have so far covered 4 approximating methods. Okay, 1, the left endpoint approximation. 2, the right endpoint approximation. 3, the midpoint approximation. And 4, the trapezoidal approximation. Okay. So this is called, so the above is called the trapezoidal approximation. Okay. This approximation symbol, right? It says this definition is approximately that. That's called the trapezoidal approximation. Oops. Okay. So that's the trapezoidal approximation. Okay. And so here, the above is called the midpoint approximation. Okay. Okay, so that's the midpoint approximation. All right, so we have the left endpoint approximation, the right endpoint approximation. You know, I'll underline it here again. This is the left endpoint approximation. This is the right endpoint approximation, 1 and 2. And I don't think I use any other symbols here. So I'm going to, okay. And then there's the midpoint approximation and the trapezoidal approximation. So we have 4 methods so far. So we've covered 4. We have so far covered 4 approximating methods, those 4. Left endpoint approximation, right endpoint approximation, midpoint approximation, and trapezoidal approximation. Let's do an example. Okay, so the example is use the trapezoidal rule. Use A, the trapezoidal rule. And B, the midpoint rule. With n equals 5 to approximate the integral to the differential from 0 to 1 of 1 over x dx. Right? Okay, so we're going to use these 2 rules in A and B. So for A, we're going to use the trapezoidal rule. Okay, so with n equals 5, A equals 1. Oh, this is a 1. This is a 2. Okay, so it's from 1 to 2. Okay, so with n equals 5, A equals 1, B equals 2. We have that delta x which is equal to b minus a over n is equal to So B and A, right, it's 2 minus 1 over n, which is 5. So this is 1/5, right? Okay, so I'm just plugging in. A is the lower limit of the lower limit. B is the upper limit, and n is given to you. Okay, that's the number of rectangles. So delta x is 1/5. 1/5 as a decimal is 0.2. Okay. Okay, so the trapezoidal rule gives you that the definite integral is approximately t sub 5. And what that's equal to is now, so we have the trapezoidal rule here, right? And so I'm just gonna, let's copy it. And so let's see how we use it here. Okay, so t sub 5 is equal to delta x, which is this, where n is 5, right? So n is 5. So this is going to be 5. This is going to be 5 minus 1, which is 4. I'll write it just directly. So that way you can see where I'm getting this from the formula. So this is equal to delta x is 0.2. So you have 0.2 over 2, and you have the bracket, right? So 0.2 over 2 times f of x naught. So you need to just plug in these values, okay? Okay, so let's go to the whiteboard for a second. So we're going to whiteboard because I want to talk about what x naught, x1, x2, x3, x4, and x5 are, and then the values of the function on those points. Okay. Okay. Note that f of x, the function we're going to use here, f of x is the integrand 1 over x. Okay. F of x is this function 1 over x, and so we want to plug in. We're going to need the values of this function f at x naught, x1, x2, x3, x4, and x5. It's t5, n equals 5. Okay, so let's go to whiteboard, and I'm quickly going to talk about those, what those values are, right? So if you have the real line, this is the real line. And so we're going from 1 to 2. We're integrating from 1 to 2. It's a definite integral from 1 to 2 of 1 over x dx. So we're going from 1 to 2, okay? N equals 5. So we're going to separate this into 5 equal subintervals. Okay, so these are 5 equal subintervals. And then I just want to know what the values are of these endpoints. Okay, so x naught is this guy. X1 is this guy. X2 is that guy. X3 is that guy. X4 is that guy. And X5 is that guy. Those are the values of x naught through x5. And so if you're going from 1 to 2, that's a length of 1. And you're moving 5 spaces. 1, 2, 3, 4, 5. So if you're moving 1 in 5 equal spaces, each time you're moving 0.2. So this is 1.2. Okay. This is 1.2. This is 1.4. This is 1.6. This is 1.8. And then when you add 0.2 to 1.8, you get the 2 at the end. So x naught is 1, x1 is 1.2, x2 is 1.4, x of 3 is 1.6, x of 4 is 1.8, and x of 5 is 2. You keep moving 0.2 to the right. If you do it 5 times, you get the 2. Plus 0.2, plus 0.2, plus 0.2, plus 0.2, plus 0.2. 1, 1.2, 1.4, 1.6, 1.8, 2. 1, 2, 3, 4, 5. See that? Okay. So those are the values of x naught. And so you're going to take f of those values, right? So f of x naught is f of 1. F of x is 1 over x. F of x is the integrand function here. So f of 1 is 1. 1 over 1 is 1. F of 1 is 1 over 1, which is 1. F of 1.2 is equal to 1 over 1.2. No, that's fine. Okay, good. Okay. And then f of 1.4 is 1 over 1.4. F of 1.6. So you see the pattern, right? Of 1 over 1.6. F of 1.8 is 1 over 1.8. F of 2 is 1 over 2. So these are the values of f of x naught to f of x of 5. 1 over 1.2, 1 over 1.4, 1 over 1.6, 1 over 1.8, and 1 over 2. The 1 is 1 over 1. Okay, and so those are the values of f at those x points. Okay, good. Okay, somebody wanted me to move up. I think I don't know. Okay, so yes, you have to say it out loud if you need help with something. Okay, so f of x naught, just plugging in, was 1. This is plus 2 times f of x1, which is 1 over 1.2. Okay. If it helps you visualize it better, I could put this is 1 over 1, which is 1. That's f of x naught. This is 2 times 1 over 1.2. The next one is 2 times 1 over 1.4. Next one is 2 times 1 over 1.6. This is plus 2 times 1 over 1.8. And then plus f of x5. That's the last one, which is just 2. Okay. This is not multiplied by 2. This is 1 times 2. 2 is f of x of 5. Okay, x naught, x1, x2, x3, x4, and the x5. And so now that value is the approximate estimation we're making of this depth integral. And so when you 0.2 over 2 is 0.1, and you add all that, you get that this is approximately 0.695635. Okay, and so we now have approximated the depth integral using the trapezoidal rule with n equals 5. That's part A. Okay, any questions about part A? Okay, so next, if you have the depth integral here again, now we want to approximate it using the midpoint rule. So the midpoint rule says that this is approximately m sub, so midpoint rule, m for midpoint rule, and then sub 5 for using 5 rectangles. And then this is equal to, well, now this is equal to the value of m sub 5. Now we're going to go back to our formula. So you can use the formula for this. M sub n is this. So m sub 5 is this when n is 5. And so m sub 5 is equal to this. I'm going to put the equal sign here. It's equal to this where n is 5. So this is a 5 here. And so instead of the dot, 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 I'm going to plug in the other terms. So, okay, 2, 3, 4, 5, good. And so now this, there we go. And so this is a 3, and this is a 4. Okay. So, so now you have that. Because n is 5, and so now you have delta x times the sum of the values of f at the midpoint of every subinterval. Okay, well we found already before the value of delta x, right? So we found delta x was equal to 0.2. Delta x equals 0.2, and so we have 0.2 here times times the sum of the values of f at the midpoints of those subintervals. So I'm going to go to the whiteboard. Then we're going to calculate these. We have x1 to x. We need x1 bar to x5 bar. Okay, so let's go back to the whiteboard. So this is x naught through x5, but this is the first subinterval. This is the second one. That's the third, fourth, and fifth, right? So this is I1, the first subinterval. And actually, I'm going to use a different color now. So when I was talking before in blue, I was talking about the trapezoidal rule. Now I'm going to use red, and red is going to be about my discussion using the midpoint rule. So this is the first interval. That's the second interval. This is the third interval. This is the fourth one. And that's the fifth one. Those are the values of x naught through x5. What we want are the midpoints of those 5 subintervals. Okay, so the midpoints of those 5 subintervals, that's x1 bar. x1 bar is the midpoint of this first subinterval I1. x2 bar is the midpoint of the second subinterval I2. x3 bar is the midpoint of the third subinterval I3. x4 bar is the midpoint of the fourth subinterval I4. And x5 bar is the midpoint of the fifth subinterval I5. And so you just find what those midpoints are. And so x1 bar is equal to the midpoint of 1 and 1.2, which is 1.1. X sub 2 bar is the midpoint of the second subinterval, which is 1.3. X sub 3 bar, which is the midpoint of the interval I sub 3, is the midpoint of 1.4 and 1.6, which is 1.5. X sub 4 bar, which is the midpoint of the fourth subinterval between 1.6 and 1.8, is 1.7. And then I sub 5, which is I sub 5 bar, which is the midpoint of the fifth subinterval I sub 5, is the midpoint between 1.8 and 2, which is 1.9. And so see, we now have 5. We have the 5 midpoints of the 5 corresponding subintervals I1 through I5, determined by x naught to x5. And so now that we have the midpoints, 1.1, 1.3, 1.5, 1.7, and 1.9, we have the values of x1 bar, x2 bar, x3 bar, x4 bar, and x5 bar. And so we're just going to plug those values in to our formula, and then we will be able to calculate the midpoint approximation of the depth interval. Okay. I just have to plug in my charger because my laptop battery is running low. 2-hour class. 1 second. Okay, okay, my laptop is charged. Okay, so we have the values of x1 bar to x5 bar. So now let's go back. All these screens here. All these. Okay, and so now, now I'm just going to plug in the values. So this was 1. So f of x is 1 over x, and so we're taking f of those values. Let me go back one more time. F of x is 1 over x. And so these are the x values, x1 bar to x5 bar, right? And so if we wanted to do f of x1 bar, for instance, f of x1 bar would equal to 1 over x1 bar, where x1 bar is 1.1. So that would be 1 over 1.1. Okay? So f of x1 bar is equal to, since f of x is 1 over x, the integrand here, right? F of x1 bar would be 1 over x1 bar, where x1 bar is 1.1. So that's 1 over 1.1. See that? And then if you had f of x sub 2 bar, it would equal to 1 over, be 1 over x sub 2 bar, which is equal to 1 over 1.3. See that? I'm just putting this separate divider here because I don't want that to be mixed up with what I did here. This is one, x1 bar is that, x2 bar is that, x3 bar is that. This is calculating. Okay, so you see those are how you get the values. It's just 1 over each of these numbers. Those are the values under F of them. Okay. Did you see what I just did on the whiteboard? You did, right? I had it on one board. Okay, good. Now I'm going to go back to the notes. And so this is 1 over 1.1 plus 1 over 1.3 plus 1 over 1.5 plus 1 over 1.7 plus 1 over 1.9. And so now you have 1.2 times that sum. And now if you put, so now you just calculate that and you round. So you get decimal, so it's an approximation. And so you get 0.69. This decimal is approximation, 0.691908. Okay, so here in B, when we use the midpoint rule, we get it's approximately 0.691908. Slightly different from 0.695635. The first two decimal points are the same, 69. The third one is different. You have a 5 here and a 1 here, and then it's different. Okay, so we succeeded in this example to use the midpoint, the trapezoidal rule and midpoint rule with n equals 5 to approximate that definite interval.
Professor,
Yeah?
what if there was like a question like that didn't specifically tell you to use a certain rule, but it said round to the nearest hundred, and then like if you use 1, then you get like if you rounded 0.695 to the nearest hundredth, it would be like 0.70, but the other one would be 0.69. Would that be wrong?
No, but when I ask questions, I'm very specific about what I want.
Okay.
So you shouldn't run into that problem. When I ask you to approximate something, you know, I might say use the trapezoidal rule, use the midpoint rule. If I don't tell you which one, then I know the approximations of them. So I wouldn't, you know, it's not wrong if using a different one. So I structure the questions so that it's not a problem. It's fine. Okay. Excuse me. So now let's look at the actual value of this function, because it's not like this function at least was chosen because it can be calculated. There's ones that can't. This one it can. And so since we can calculate, we can compare the actual value to our approximated values. So this definition from 1 to 2, 1 over x dx. This is equal to ln of the absolute value of x evaluated from 1 to 2. Right? And so then that's equal to ln of 2 minus ln of 1. ln of 1 is 0, so this is ln of 2. And that's equal to 0.693147. Okay. 0.693147. And so you see how it's different than the midpoint rule approximation. The first two decimal points are the same. Instead of a 1, there's a 3. Here, the 6 and 9 are the same, but instead of a 5, it's 3. So you actually see that the actual value is kind of like sandwiched between the midpoint rule and the trapezoidal rule. You have a 5 here and a 1 here, and then the actual one is a 3 there. It's not exactly in between, but it's close to being in between. Okay, so we see that the actual value is different than our two approximations, right? And so let's talk about how good. So the next question is, how can you measure how good an approximation is? Okay, right? So when you approximate something, you're not finding the actual value, you're approximating it. And so a good thing to know is how close your approximation is, right? Your approximation is 100 away. In this application, it's useless, right? So you need an approximation that you know is close. And one way to know it's close is by being able to calculate the difference, or in a sense, have a bound for the difference, okay? So we can know how good our approximation is by knowing that the difference between the actual value and the approximation is at most a certain number, okay? Knowing the exact value would be silly, because then we would be calculating the actual value. But when we have an approximation, we can sometimes say that the difference between the actual value and the approximation is at most a certain amount. So we know we're within a certain range of the actual value. by our approximation. Okay. Okay, and so the question is, how can you measure how good an approximation is? And so that's the goal. Okay. Okay, so let's to get to that answer. Let's first talk about the definition of an error. So if you have a differential from a to b of f of x dx, you can say it's equal to your approximation plus the error in your approximation. Okay. So this differential is equal to your approximation plus the error of that approximation. Okay. So the error, we'll move this down. Okay. So the error using an approximation is defined as the amount that needs to be added to your approximation to make it exact. Okay. So from our values in the last example, we see that the errors in the trapezoidal and midpoint rule approximations for n equals 5 are, and so here I'm going to use a new notation, E sub r is the error using the trapezoidal approximation. So that's approximately negative 0.002488. So the error can be negative. Here it's negative. And E sub m, so this is a little easier because m stands for midpoint rule. R is standing for trapezoidal rule, okay? And E sub m is approximately 0.001239. Let me quickly good, it's a 9. Okay, good. Okay. Right. So from our values in the last example, so what does that mean? Okay, so the actual value is this with the dot, dot, dot. Okay, reminder. The actual value of our definite rule was that. So the actual value of the definite from 1 to 2 of 1 over x dx was this. Okay, so the actual value was that. Then the trapezoidal rule approximation is equal to, and so of the same integral, that was equal to this. And the midpoint rule approximation was equal to this. Okay, so you have the actual value, you have the trapezoidal rule approximation value, and the midpoint rule approximation value, right? We're defining the error to be the actual value equals the approximation plus the error. And so if the actual value is this, it's equal to the approximation, which is this for the trapezoidal rule, plus the error using the trapezoidal rule. Okay, so you have this equation. You have that the actual value of that f integral is equal to the trapezoidal rule approximation plus whatever the error is for that trapezoidal rule approximation. Okay, and then solving for E sub r, you get that's equal to that. Yeah, it's approximately that. Solving, you get E sub r is approximately that. So if you take this amount and you add that one to it, you get that. 5 goes to 3. See, or you would solve for it. You'd do E sub r is equal to 0.693147 minus 0.695635, and then you would get that. So you see? So by this definition of error, if you have, if you know the actual value and you know the approximation, you can subtract them to get the error in your approximation. That's how we found E sub r here. Now also, if you have the actual value again, that's equal to, right? The actual value is equal to the approximation, which in this case is the midpoint rule approximation, plus the error in your approximation for the midpoint rule, which is E sub m. And then solving, you get that E sub m is approximately E sub m is approximately this. Okay, this is from our values in the last example. So we had the actual value, which is this guy, is equal to, by this formula, by this definition, the approximation using the midpoint rule plus the error using the midpoint rule. Okay, and so how to get the error in the midpoint rule approximation. E sub, well, this is the trapezoidal rule approximation. So how to get the error in the trapezoidal rule approximation called E sub r. Okay, that's this. And then how to get the error in the midpoint rule approximation called E sub m. Okay, so sometimes you might get confused which is the trapezoidal, which is the midpoint. I've set it up here, but I'm just writing it clear here. Okay, and so you just use the above formula, the above equation, and you plug in the values. You know, if you know 2 of the 3 values, you know the third, and so you can find the errors in the 2 approximations. Okay, and so that's illustrating how you calculate the error. Okay. Okay, in general, we have that if you have the error in the trapezoidal rule approximation, it's equal to our definite integral from a to b of f of x dx minus the t sub n, which is the trapezoidal approximation. Okay, so the error in the trapezoidal rule approximation is equal to the actual value minus the trapezoidal rule approximation. And I'm going to write something to explain that a little bit more underneath. First, I just want to write this. The error in your midpoint rule approximation is equal to the definite integral from a to b of f of x dx, the actual value, minus the midpoint rule approximation. Okay, this is saying that the error in your trapezoidal rule approximation is equal to the actual value minus the trapezoidal rule approximation. Okay. I'm not going to abbreviate. Okay, so then this is going to be equal to the actual value minus the trapezoidal rule approximation. Okay, that's this one. And then you know what? I'm going to move this underneath. And you also have this equation. And so you have that one. And what that says is that the error in the midpoint rule approximation is equal to the actual value, which is this guy, minus the midpoint rule approximation, which is M sub n. M sub n is when you add up n rectangles using the midpoint rule. That's your midpoint approximation, midpoint rule approximation. Okay, saying error equals actual minus approximation is just directly from this formula. Error equals actual minus approximation. You're just rewriting this equation as an equivalent one, where instead of solving for the actual value, you solve for the error. Instead of actual equals approximation plus error, you'd say error is equal to actual minus approximation. It's defined this way, though, because you'd rather define it in terms of addition than in terms of subtraction. Okay? And so it doesn't make much difference. Okay, so then, so that's explaining in general what we have. We have this in general, and we also have this in general. Okay, so if you look on page 349, it'll show you tables for approximate values of that depth interval we just discussed. And so, okay, so on page 349 of the textbook, Stewart, right? The Stewart book for calculus this class. On page 349 of the textbook, there is a table of approximations of the depth integral from 1 to 2 of 1 over x dx. Okay. So you can look at that table and see values of approximations. Okay. Okay. Okay, so there are several things that you kind of see. It's not proofs, but for the table you can visualize some things. I just want to make a point of one thing that you can notice about these approximation methods. Okay, in all of the methods of approximation, when we increase the value of n, we get more accurate approximations. Okay, so in all the methods of approximation, when we increase the value of n, we get more accurate approximations. There are other observations to make, but they're not that important. Okay, maybe I'll make another one. Okay, so this is the third thing in the book. Okay, so the third thing in the book is that the trapezoidal and midpoint rules are much more accurate than the endpoint approximations. Okay? Okay, and so usually you'll see that they're much more accurate. Okay. Okay. And so then the other ones that we don't have to. Okay. Okay, and so now let's talk about the bound of our error. Okay, I was saying before about how when you make an approximation, you can bound the error, and in that way you can see how close your approximation is to the actual value. Okay. Okay. So this, okay, the 2 points below are in reference to the table of approximate values of the definite interval above. Okay. So when it says that the trapezoidal rule and midpoint rules are much more accurate, it's referring to this definite interval. And in this one, I'm still talking about the definite interval there. Okay, so just to make sure this, it's in reference to that definite interval. Those are the two that kind of matter more. Okay. So let's talk about the bound of our error. Next class, we'll talk more about this. So the error bound, that's what it's called. Suppose when you take the absolute value of f double prime of x, the second derivative of x, is less than or equal to k. Okay, for x between a and b inclusive. So for a less than or equal to x, less than or equal to b. If E sub r, the trapezoidal rule error, the trapezoidal rule approximation error, and E sub m, the midpoint rule approximation error, are the errors of trapezoidal and midpoint rule approximations, then we can say they have these two inequalities. The absolute value of E sub r is less than or equal to the fraction k times b minus a squared over 12n squared. Okay. And the absolute value of E sub m, the error in the midpoint rule approximation, is less than or equal to the fraction k times b minus a squared over 24
It's cubed.
n. Yes, it is. It is cubed. Thank you. Okay, over 24n squared. That's cubes. Okay. Cubed. Cubed. Yep. Okay. Fix that.
Professor?
Okay. Well, just give me 1 second. Okay.
All right. That's fine.
Okay. So for error bounds, we have this, right? So suppose the absolute value of f double prime of x is less than k for all a there, and then for these errors, we have these upper bounds. Okay. And so this is how, when you make an approximation using the trapezoidal rule or midpoint rule, you have an upper bound for the error of that approximation. And so that means the goal should be to have this to be small. If you can have this upper bound to be small, then that means that the error is at most a very small number. This that means that your actual value is very close. Your approximation is very close to the actual value. Okay, so that's the goal of error bounds here. And so next class we will talk about, we will talk about error bounds and finish 6.5. Okay, and so that's the end of class. There's no new homework because we didn't finish this section. So there's no homework for next class. Okay, so no homework for Wednesday. Okay, so you have a question?
Yeah. Like, will we have to prove anything like this? Because like I hope not, because this looks very complicated and stuff like that.
There are problems where you use it. So we'll talk next class about what you need to know about it.
All right.
Okay, there's no homework though, so you don't need to use it yet.
All right. Thank you.
You're welcome. Okay, so that's the end of class for today, and I will see you all on Wednesday. Bye.
Thank you, Professor.
You're welcome. Have a good one.
You too, sir.
Bye, everybody. You too, Nicole. Bye. Okay, bye.